Hello, and welcome to your decision tree lecture in Python. So as usual, the first thing we're going to do is run all of our import statements to make sure those are there. And then let's load in some of our data. So this should look a little bit familiar. We have a data set where we have whether or not a transaction is fraudulent, whether or not it was in someone's home region, the amount of the transaction, and then whether or not someone had cash back with that transaction. So we are going to use this data to build a decision tree to predict whether or not something was fraudulent. So again, our workflow for building this model is very similar to all the models we've done previously. First, we're going to set apart our X and our Y variables, and then we need to decide what type of model validation we'd like to do. So in this case, I'm going to do a train test split. So let's get that code in here. And I'm going to get our train, our test for Y and X. And once we have that, now we can actually do any of our pre-processing that needs to happen, for instance, like z-scoring, without data leakage, because we can only train them on the training set. So I'm going to create a z-score object, standard scalar, and I'm going to go ahead and fit it, z-score.fit, but we need to think about the fact that of our predictor variables, not all of them are continuous, and we only z-score continuous variables. So unlike before, we need to make sure that we're specifying that there's only one column that we'd like to z-score, and that column is the amount of the transaction. So the way that we can do that is at first looking like we've had before with z-score.fit, but now we're going to say only z-score.fit X train amount. So we're going to calculate the mean and the standard deviation necessary to z-score amount, and then everything should look pretty similar. So we're going to say X train bracket amount. So we're saying out of the original data frame, only replace the amount column because none of the other ones are getting z-scored. And then we're going to say z-score.fit, or it's not fit, excuse me, transform X train amount. And then I'm going to go ahead and copy and paste, because it's the exact same thing, to do it for the test set. And then we have our z-scores. So now that we have our z-score data incorporated into our data frame, we can go ahead and create a model. So I'm going to call mine tree and set that equal to decision tree classifier. And then we can go ahead and fit our tree. So we can say tree.fit X train Y train. And again, X train now has our z-scored amount column, and all of the other variables have been left alone. All right, once we go ahead and run this code, and we have to spell that correctly. Once we run that code, we'll have a trained decision tree, and now we can assess how well our model is performed. So the first thing that we're going to do is we're going to grab our predicted values. I'm going to store them in the ypred variable, and I'm going to say tree.predict x test, and then we can use those values to generate an accuracy score, because remember, like logistic regression, decision trees are outputting a categorical prediction, so we can see how often it guesses the correct category, fraud versus no fraud. So we can do that with the accuracy score, and again, we're going to need to give it our actual values and our predicted values. And when we print this out, you can see that we have actually pretty good, about an 87.5% accuracy. But as we've learned before, we might want a more nuanced picture of what's happening. So we can use the plot confusion matrix, there we go, function. And that takes in our model, it takes in our predictors, and then our actual values, and this will give us similar information to the accuracy score, but with a lot more detail. So let's go ahead and run that and look at our beautiful confusion matrix. And so you can see the first thing that we look at is the main diagonal, which tells us how often we were accurate. So it looks like there were 18 times when the true label was no fraud and there actually wasn't fraud, and there's 17 times in our test set at least where we predicted fraud and it was fraud. And you can see on the off diagonal, we actually didn't make that many errors. So there were 5 errors total, and the errors look pretty balanced. So I don't see anything as a part of this confusion matrix that's really concerning to me. So I'm going to go ahead and move on. So in our lecture, we talked a little bit about the depth of a tree, which is the depth of the tree at the deepest point. How many layers do you have to go through? So let's see how deep our tree is. We're going to say tree.getDepth. There we go. And let's run this. Okay, so our tree has 9 layers at its deepest point, which is not that deep, but given we only had 3 predictor variables, is pretty deep. And we can also see how many leaf nodes we have. So we can say tree.getNleaves. And when we run that, we can see there's 34 terminal nodes. So there's 34 leaves on our tree. And we talked a little bit before about how decision trees, when they get very deep, can be a little bit overfit. We're basically getting a little too specific to our training data and maybe aren't doing as well in our testing data. And so you can actually artificially limit the depth of your tree. You can basically set a maximum depth. And the way that we do that is just by adding an argument for the maximum depth that we want. So I'm going to go ahead and copy our model from the previous section. And I'm just going to add max depth equals, let's say 5. So now, instead of 9 layers, which is what this tree originally created, the maximum depth of our tree is going to be 5. So let's go ahead and refit that. We're going to say tree.fit x train y train. And then let's run that. We can go ahead and grab our predicted values like before. We're going to say tree.predict x test. And then we can again grab an accuracy score. So let's do that now, accuracy score. And then we're going to say y test, y pred. And so when we run this, you can see that our accuracy is now 92.5%. And just to double check, let's go ahead and say tree.getDepth to make sure that our maximum depth worked. So we're going to run that. Beautiful. So we have 5 layers at our deepest point, which makes sense because we said the maximum was 5. Technically, we could probably have less than 5, but we would have at least no more than 5 layers. Next, we've seen our accuracy score, but let's go ahead and look at our confusion matrix. So we're going to say plot confusion matrix, and we're going to give it tree, we're going to give it x test, and then we're going to give it y test. So let's look at our confusion matrix. Beautiful. So again, we're looking at that main diagonal to tell us whether we got things correct, which we most often did. And then we're looking at the off diagonal to see what errors we made, and we're going to check for any weird patterns. But again, I don't see any here. The errors are roughly balanced. The correct values are mostly balanced, and there's not like a single column or row that has like all zeros. So I'm thinking that this looks pretty good. So the interesting thing here is we actually made our model less complex. We limited the complexity of our model because we limited the depth of our model. And the fact that we still got really high accuracy is basically pointing to the fact that we can have a less complex model that actually fits better on unseen data, even if we sacrifice a little bit of training accuracy. Limiting the depth is a great way to generalize our models from our training set onto unseen data. All right, the last thing that I want to touch on is something that we're not going to dwell on too much in this class, but may be useful to you later on in your data science career, and that's feature importances. So I'm going to go ahead and grab those from our model, and basically you get 1 feature importance score per predictor in our model. So we have 3 predictors, which means we have 3 scores here. And the higher the score, the more important a feature is at helping the model to make predictions. So the highest score is the most important feature here. And while we won't use them a ton, feature importance is really interesting. And for instance, I've been reading some papers that suggest that you can use feature importance from a decision tree or a random forest to do something called variable selection, where you decide which variables, which predictors to go in your model. Now, we'll talk about other ways to do variable selection later on in the semester, but I just want to throw that in here because it is something that might be useful to you later on. All right, let's do one more example. So I'm going to go ahead and run this data, and this is heart data. So we're predicting basically whether or not someone had a heart event. It's from the target variable based on all of these other kind of like biological or measurement variables. So let's go ahead and build a decision tree, but let's go ahead and build one inside of a k-fold for loop. So the first thing that we have to do as always is say which our predictors are. I'm going to store them in a list to make our lives easier. And then we're going to need to go ahead and set our x and y. So I'm going to say heart predictors, and then I'm going to say y equals heart target because we're trying to predict the target column. And then, as usual, I'm going to create my k-fold object, k-fold. And let's go ahead and do, let's say 5-fold. Well, let's do 4 because we don't have a ton of data. 4 folds. And let's go accuracy equals empty list so that we can store our test accuracies. And then I also am interested in looking at the depth of the tree, so I'm going to create a list for that metric as well. Okay. Let's build our k-fold for loop. The first part, again, should look very familiar. We're setting our x test or x train, y test, y train. And now the next thing that we can do, now that we have our train and our test set separate, is we can do any z scoring we need to do. So I'm going to say z equals standard scalar. And then I'm going to say x train equals, actually x train. So remember, in this data set, similar to before, not all of our variables that we're using as predictors are continuous. For instance, sex in this case is treated as a binary variable. And so we need to make sure that we're only z-scoring the variables that are continuous and not the ones that are categorical. So in this case, the variables that are categorical of our predictors, sex, age, rest, ECG, and cholesterol, are age and cholesterol. So I'm going to go ahead and use fit transform in order to do my fitting on the training and transforming at the same time. So I'm going to say z.fit transform, there we go, x train, age, oops, not capital, and cholesterol. And then I'm going to go ahead and do something similar to the test set, but remember, we never want to refit on the test set. So this is just going to be x test age col equals z dot transform x test age col. Again, so we're not refitting on our training or our testing set, excuse me. Okay, so now that we have our z scoring, let's go ahead and build our model. I'm going to say tree equals decision tree classifier. And then we're going to say tree.fit x train y train. And remember, x train now has our z-scored variables as well as the completely left alone non-z-scored categorical variables. And now I'm going to add our accuracy to that empty list that we created before. So I'm going to say acc.append, and I'm going to say accuracy score. And I'm going to give it the actual values. So I'm going to give it test, and then the predicted values, which is tree.predict x test. And then the other thing that I wanted to grab from my model is the depth. So I'm going to say depth.append, and I'm going to say tree.get depth. So that's just going to tell us how deep each of the decision trees that we fit is, because remember, we're fitting 4 of them because we have 4-fold cross-validation here. Now, the last thing that I just want to look at, and I'm not going to store it anywhere, but I do want to see them, is the confusion matrices. So I'm going to say plot confusion matrix, and then I'm going to say tree, x test, y test. So this isn't going to store anywhere, but it will print out the confusion matrix for each model that we build. All right, once our k-fold for loop is done, I'm going to want to see the average depth and the average accuracy. So let's go ahead and print out np.mean acc. And actually, maybe instead of the average, I'll just print out all of the depths since there's only 4 of them. So let's go ahead and run our k-fold decision tree. Oh, and spelling standard scalar correctly would probably help. Standard. All right, let's go ahead, rerun that. Okay, so we have our average accuracy, not great at 48.8%, and our average, or not our average, all of our depths. But let's look a little bit at our confusion matrices. So I've been saying this entire time since logistic regression, we want to check our confusion matrix for weird patterns. Well, it looks like we are seeing a weird pattern here. You can see that in the 4 folds that we have, in the first 2, this entire column, the top column, are all zeros. And if you think about what that means the true labels, there were no true labels in the test set that were 0. And in the same case, that happens here. In the 3rd decision tree that we built, we actually see a confusion matrix that looks more typical to what we would expect to see. But then we actually see the opposite problem in the last one, where there's no 1s in the testing set. And this is a pattern that should be very suspicious to us. That means that the top 2 folds have no 0s in them, and the bottom fold has no 1s in it. Now, this is something that can happen depending on how the structure of your data is set up. So if for some reason your data file has all of the positive cases at the top and all the negatives at the bottom, or vice versa, you can wind up with a situation like this where some of your folds don't have any 0s, or some don't have any 1s as the outcome. And that's not super helpful to us because we're basically in a situation where our model is not being tested on whether it can predict positive cases, or in the case of these top 2, it's not being tested on whether it can predict negative cases. And so one thing that we can do to prevent this from happening is in the k-fold function, we can set the argument shuffle to true. And basically what this does is when you think of your data frame with all of its entries, it shuffles the rows around before creating folds, so that if your data is structured in a way where you're going to get test sets that don't have any 0s or don't have any 1s, this prevents that largely from happening. So let's go ahead and rerun our code with this shuffle argument on. Beautiful. Okay, so now we can see that we have confusion matrices that look a lot more like we would expect them to look like. So when you scroll through here, you can see that we don't see that weird pattern anymore. In fact, all of these look pretty good, right? We have a lot on the main diagonal, which means we're getting a lot of our entries right. And we don't see anything else weird. We don't see a huge imbalance of errors or anything like that. We can just see that our model is, doing about 60% accuracy, which is exactly what the accuracy score told us. So this is why it's really important to look at confusion matrices, because sometimes there's going to be weird patterns that you see that you can't even assess using just the accuracy score alone. Okay, that is all I have for you. I will see you guys next time.